Next, we're going to talk about something called the greatest integer function. And the greatest integer function has bars around it that kind of looks like this stuff right here. And you may or may not have seen it. And as we look at this, I will draw a picture for you of this greatest integer function. So as you look at the picture, I'm going to draw my picture just a little bit bigger here so you can see what's going on. So here's a x and y axis. And let's just say I had 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And these are going up by ones. And if I pick some values in here, the greatest integer function says that the answer that comes out can be an integer less than or equal to the integer that you give. So for example, if I'm drawing this picture, this is what I would see. Okay, to give that example in our chart, what you would see in the chart is you would see, oh, if I plug in a 0, out pops a 0. If I plug in 0.5, out pops 0. Because 0 is the integer less than or equal to 0.5. If I put in 0.9, I still get out a 0. If I put in a 1, I can get a 1 out. If I put in a 1.2, I get out a 1. If I put in a 1.99, I still get out a 1. Once I put in 2, I get out a 2, so on and so forth. The only caution is if you put in negative. So like for example, if I put in negative 1/2, the number that's less than or equal to negative 1/2, that's an integer, is negative 1. So keep in mind, greatest integer means give me the integer, no fractions, no decimals, that's less than or equal to the number that you see. That's greatest integer. Piecewise, we talked a little about yesterday, and we talked about the fact that the stuff that's on the right-hand side, these things are called the conditions, and that actually what I want to talk about is the stuff that's not the condition, which happens to be the function themselves based on the condition. So one of the things I always like to tell people is you should make two tables, and both tables should start with the condition. So let's look at what I'm going to call the red table. This red table is going to talk about the x squared part. So x and y. The condition was the 0, so I'm going to start with 0. And then if you look in the green next to the x squared in red, it says you want numbers less than 0. So those would be numbers like negative 1 and negative 2. So I take these numbers that I have in x's and I plug them into the red stuff. So 0 squared is 0. Negative 1 squared is 1, negative 2 squared is 4, and this is my red table. Come up with 3 points. In my blue table, I'm going to take the other stuff, the 3x minus 1, and I'm going to make another table that says x and y. I'm still going to start with 0 for the x. So I'm always starting with the condition for the x. So here's the x for the condition, here's the x for the condition, the same as the highlighted stuff up there. And now I plug in the numbers. So I plug in 0, but it tells me in the condition to go bigger than 0. So I'm going to pick 1 and 2 for the x values, because those are ones bigger than or equal to 0. And if I plug in a 0 into the blue, 3 times 0 is 0, minus 1 is negative 1. If I plug in a 1, 3 times 1 is 3, minus 1 is 2. And then if I plug in a 2, 3 times 2 is 6, minus 1 is 5. And what I'm going to do is I'm going to graph these things to the right. And let me just show you what it looks like. So here's my graph. I'm going to extend it out a little bit so I can see it. Notice I go from negative 2 to 1, positive 2 on the x-axis. So as I do that, here's my negative 1, here's my negative 2, here's my 1, and here's my 2. And then I have to have numbers as high as 5 and as low as negative 1. So 1, 2, 3, 4, 5, negative 1. Let's graph the red first. Notice that in the conditions, it said that x is less than 0. So this point 0, 0 doesn't actually exist because it has to be less than 0. So I'm going to put an open circle there. So I put an open circle at 0, 0 for the red, because it did not have an equal sign for the condition. And then I'm going to put the point -1, 1, which is a solid point. And then I'm going to put the point -2, 4, which is also a solid point. And you can see that this is the left side of a parabola. In the blue, on the other hand, since there was the condition x greater than or equal to 0, I can put a solid dot at 0, -1. So I do that. And then I have another dot at 1, 2. And another dot at 2, 5. And this is a line, as you can see, going up and to the right. And this is a graph of my piecewise function. And so the big idea is whenever you have a piecewise function, make sure that you do two different tables. I would color code them. Always start with the condition and add two more places. If there was an equal sign, it's a solid dot. If it was not an equal sign, it's an open circle. Okay, last page. Even and odd. I don't actually like to do these things for even and odd. And what I want to show you is there are a couple rules for even and odd. And the big rules are, if you have an even function, when you plug in the opposite of x, out pops the original function. I'll talk about more of that with my examples. I have two of them. And if it's an odd function, then when you plug in the opposite of x, you get the opposite of the function. So let me just pick my own screen here and show you the two functions that I like to talk about with this even and odd thing. The first function is when my function f of x is x squared. So let me just show you what that means. First of all, a picture of this x squared graph looks like this. We have a picture that is a parabola. And when I try to figure out whether it's even or odd, I always plug in opposite x. It doesn't matter if you're testing for even, it doesn't matter if you're testing for odd, you always plug in opposite of x. What does that mean? That means that I know that I have the function x squared. And what I'm going to do is I'm going to shove in opposite of x and see what happens. So I put in opposite of x here. What does that mean? That means I have -x times -x, which turns out to be x squared. What I want you to notice is that this ending result, when I plugged in the -x, is indeed the exact same thing that I started with. That means that my answer is that this is an even function. If you end up with the exact same thing you started with, when you plug in -x, it's an even function. The other thing that's kind of cool about an even function is visually you can tell, because if you look at this red graph, this parabola, it is mirrored over the y-axis. So if you can fold a graph over the y-axis and have it match up exactly on itself, it's an even function. On to the odd functions. The odd function works the same way. The one I like to use is f of x equals x cubed. If we look at a picture of this function, what you will see is it looks something like the following. So this is our standard cubic graph. What happens? Same idea. We are still going to plug in the opposite of x to test whether or not this is an even or an odd function. So my function was something being cubed. What do? I take that opposite of x and I shove it in there for the function and see what happens. So this means I'm taking -x times -x times -x, which means I have -x cubed. And what you should notice is that this was the function that I started with, and since my end result is the exact opposite of what I started with, this is telling me that I have an odd function. Because I started with x cubed, I end up with opposite of x cubed after I plugged in -x. The cool thing about an odd function is if you look at the picture, what you will notice is that it is pinwheeled around the origin. So here's my origin right here, and I spin it around. So basically this means it's been reflected over the x-axis and reflected over the y-axis. That is an odd function, 2 reflections. The even function was just over the y, the odd is over both. I hope this worked out for you guys. Sorry I'm not here for you. We'll talk to you later.